The cloud is often described as a weightless, invisible layer of digital services. In reality, data processing is a massive, heavy industry, anchored by acres of steel, concrete, and high-voltage hardware. The math behind artificial intelligence forces a new scale of resource extraction. A standard search query requires 4,000 bytes of data, but generating a single high-definition AI image demands 2 megabytes. As these requests scale into the millions, compute requirements are exceeding the limits of existing facilities. This chart shows the projected energy consumption of United States data centers. By 2028, these facilities are expected to double or even triple their power draw, capturing up to 15% of all available electricity on the national grid. The traditional power grid cannot support this load. Utility companies are physically unable to generate or deliver electricity fast enough to meet the timelines required by AI training schedules.
Today, they have hit a physical wall. To secure the electricity required to survive this bottleneck, hyperscalers like Google, Meta, and Amazon are moving beyond their historical role as passive corporate consumers. They are becoming energy developers. Training a frontier AI model requires continuous gigawatt-scale baseload power. To keep the chips running, the facility must have a captive supply that stays on 24 hours a day. Historically, industrial projects relied on regional utility monopolies to supply this electricity, but these utilities operate on highly regulated rate bases, making them slow and risk-averse. Furthermore, these regional grids are already strained by federal mandates to slowly decarbonize their infrastructure and retire aging coal-fired power plants. Technology giants are using their balance sheets to bypass the utility monopolies. They are directly funding the construction of next-generation small modular reactors. Meta has agreed to fund TerraPower units, providing 690 megawatts, and signed a deal with Oklo for a 1.2 gigawatt nuclear campus. Amazon is working with X-Energy on a 5 gigawatt pipeline, while Google has committed to its first small modular reactor by 2030. Building experimental nuclear technology involves significant construction risks and potential cost overruns. By absorbing these risks directly, hyperscalers create the revenue certainty that commercial banks require before they will issue construction debt. These companies are trading billions of dollars in upfront capital exposure for direct control over their own power supply. Generating localized nuclear power only solves half the equation. Connecting that power to the data center facility has hit a separate infrastructure wall. This chart highlights the supply chain bottleneck. The red area shows the volume of data center buildouts facing connection delays through 2030, driven largely by a single constraint. Procuring conventional medium-voltage iron core transformers currently requires a 3-year lead time. Conventional iron core transformers rely on heavy copper windings and output fixed alternating current. Their physical weight and manufacturing complexity lack the required versatility for rapid AI deployment. This diagram compares traditional distribution with NVIDIA's 800-volt direct current architecture. Pushing power at a higher voltage reduces required wiring by 70%, freeing rack space for GPUs. To work, electricity must be converted directly from the medium-voltage utility network into that 800-volt DC bus. This is achieved using solid-state transformers. These power electronics devices convert the voltage directly, eliminating the need for massive iron cores and the 3-year waiting list attached to them. By redesigning the internal electrical architecture around solid-state hardware, tech companies compress deployment timelines and bypass the utility interconnection backlog. Replacing tons of iron with compact electronics requires highly specialized semiconductor materials capable of managing medium to high voltages safely. This schematic details the converter cells inside a solid-state transformer. Standard silicon fails here, so engineers use silicon carbide, which operates above 10,000 Hz. This rapid frequency allows magnetic coils to be drastically reduced in size, achieving 99% conversion efficiency in a fraction of the space. This translates into physical hardware, like this high-voltage power module. These compact, copper-plated silicon carbide components act as the true engines of the AI power stack. Without the exact atomic properties of silicon carbide, building a physical bridge between a gigawatt nuclear reactor and a high-density AI compute cluster would be impossible. Once that clean 800-volt DC power reaches the compute rack, thermodynamics presents a final barrier. The electricity is immediately converted into concentrated heat. Next-generation AI GPUs are pushing power densities to incredible extremes. Historically, a standard server rack generated around 10 kilowatts of heat. Today, that number is surging toward 132 kilowatts. Traditional air cooling fails under these conditions. Air lacks the thermal conductivity to absorb and move that volume of heat fast enough to protect the silicon. Air systems also create a parasitic power drain. Embedded fans must spin at maximum velocity to keep up, consuming massive amounts of IT power themselves and decreasing the facility's power usage effectiveness. The required upgrade is direct-to-chip liquid cooling. Liquid carries heat away far more efficiently, shifting the thermal management workload from node-level fans to a centralized chilling system. This chart from Supermicro illustrates the difference. During high-intensity workloads, an air-cooled node draws 6.2 kilowatts. The liquid-cooled node draws 5.2 kilowatts. That 1 kilowatt reduction yields a 16% savings in total node power. Scaled up to a 5,000-node hyperscale cluster, this cooling adjustment saves over $11.8 million in energy costs every year. It also provides a direct operational boost. Maintaining strict temperature control allows the GPUs to run faster, unlocking up to 17% higher computational throughput during intense stress tests. Liquid cooling has shifted from a passive environmental measure into an active, critical design variable required to make hyperscale AI financially and physically viable. The complete thermodynamic architecture of AI relies on 3 precise layers: direct-to-chip liquid cooling at the server, silicon carbide solid-state transformers at the substation, and gigawatt-scale modular nuclear reactors at the source. But this multi-billion-dollar redesign introduces a severe economic complication known as the Jevons paradox. In the 19th century, economist William Stanley Jevons observed that as technological improvements increase the efficiency of using a resource, the relative cost drops. Instead of saving the resource, the cheaper price drives the total rate of consumption up. Applying the Jevons paradox to the data center reveals a compounding cycle. As silicon carbide electronics and advanced liquid cooling make these systems highly energy efficient, the unit cost of AI compute drops. This cheaper compute instantly incentivizes tech companies to train exponentially larger foundation models. They order more facility build-outs to house them, which pushes the aggregate power demand even higher. The engineering triumphs achieved at the micro level of the silicon chip guarantee that the macro-level energy grid crisis will continue to escalate. To secure their AI future against the laws of physics, software companies have evolved into heavy industrial conglomerates, physically rebuilding the power grids of the 21st century.